Coulomb's law, if you remember, relates the force between two charges or two charged particles based on the distance between their centers. Now sometimes that'll be an R, sometimes there's an L there, sometimes they use a D. Basically the distance between the two charges 1 and 2. And this will be a force. It is a vector, so it has direction, so depending on the charges plus or minus, or both positive, both negative, it'll have a attractive or repulsive. So let's just do an example here. Real simple. We're going to have a plus charge here. Let's say it's a meter away. We're going to have a minus charge here, and let's make it 2 meters away. Let's have another plus charge. Now I'm going to just pick some random numbers here. Let's make this 10 microcoulombs. We'll make this 20. Hello. Make this 20 microcoulombs, and let's make this 40 microcoulombs. Now, what we want to do is find out what's happening to this charge in the middle. Which direction, what's the net force acting on it, and things like that. So this is Coulomb's law. It's the force between. So we're going to look at this charge in particular. Now the first thing I like to do is just draw out the direction that each one will. So if this is charge 1, that's charge 2, that's charge 3. The effect that charge 1 has on this center charge 2, it's attractive because they're opposite, so it's going to try to pull that way. So we can call it the force of 1 on 2. And obviously, because of Newton's third law, equal and opposite, 2 would pull back on 1 also. But we're not worried about what's happening in 1. We're going to look at 2. Now 2 won't pull on itself because of it can't. And 3 is opposite, so it will pull it 2 towards 3, and this will be the force of 3 on 2. So if we want to know the net force or resultant force on 2, basically what we're adding up is the force of 1 on 2 plus the force of 3 on 2. Now, if we're going to pick positive to the right, what happens is 1 on 2 becomes a negative pull, and we think of that as in the positive direction. So when we add those vectorially, we have to keep that sign in mind. So how do we find the individual charges there, or what the individual forces? Well, the force of 1 on 2 is using Coulomb's law up here. So it'll be 9 times 10 to the 9th. On top, we're going to have the two charges. 10 times 10 to the minus 6 coulombs, that's micro, 10 to the minus 6 is micro, times 20 times 10 to the minus 6, that's 20 microcoulombs. The distance between is 1 meter squared. I made that so it'd be easy math. Now, the easiest way to deal with all this exponential stuff is multiply all the prefixes. I don't know if that's the correct word mathematically, but I'm going to multiply the 9 by the 10 by the 20. So that's 200. That should be, I think, 1800. And then what I'm going to do is grab all the scientific notation. 10 times 10 to the 9th times 10 to the minus 6 times 10 to the minus 6. Now when we multiply those, we will add exponents. That becomes 10 to the 9th minus 6. That becomes 10 to the 3rd. That becomes times 10 to the minus 3. So move it over 1, 2, 3. That becomes 1.8 newtons. Now that is that direction. Okay? So we do the same thing for the force of 3 on 2, and that's going to be, I'll write out quick, 10 times 10 to the 9th, and up here we're going to have the 20, and we'll have the 40 times, and over to 1. So real quickly, 80 times, was that 720? 7,200 times 10 to the minus 3rd, 7.2 that way. That gives us a net, if we go through that, a minus 1.8 newtons plus 7.2 newtons that direction. That gives us a net of 5.4 newtons that way. I'm sure you'll yell at me if I did the math there wrong, but just trying to keep close. Hopefully you understood that, and we'll see you next video.